The bisection method is one of the most idiosyncratic algorithms when you start looking into your computer science courses. And one of the reasons why it is so traditional maybe lies on the fact that it demonstrates very clearly and elegantly the fact that a small change in how we address a problem can have severe consequences on execution times. So here we have a very simple question. How does a computer calculate the square root of a number? So let's suppose that we have the square root of 25 to calculate. Now, some of you, the most prominent mathematicians, can probably guess that this is the value of 5. Now, how can we make the computer calculate this number, however? The bisection algorithm is based on the principle of discarding half of the information between different iterations during the execution of that algorithm. And the general idea is to have three main components, named the minimum value, which usually starts at 0, the maximum value, which is initially set to a target, which is going to be the value from which the square root has to be calculated, in this case 25, and then a candidate number. Now, what would be a good place to start guessing on candidate numbers? One thing that we could try is dividing the maximum number in half. That would be our candidate. 25 divided by 2 is 17.5. What we can do then is raising the candidate to the exponential 2 and see if that gives us the value 25. 17 exponential 2 is definitely bigger than 25. So here we can discard the right half of this graph right here. So we are certain that if 17.5 is squared is too big, way bigger than 25, which is the target, no number bigger than 17.5 can also be a candidate. Therefore, we rescale and reassess our statement by making the current candidate the new maximum. And we repeat the process. This time, we set the candidate to half of 17.5, which is 8.75. Well, 8 times 8 is 64, which is bigger than 25. We know that's not the case either, but we get the gesture of it. We can set the candidate as the new maximum, and then repeat the process. This time, half of 8.75 is 433, is 4.37. So 4.37 squared is going to give us a value that is smaller than 25. So it seems that this time we missed it not by being too big, but by being too small. So how can we recalibrate in this case? The candidate this time is not going to become the maximum, but rather the minimum. No value before the minimum raised to the square is going to be exactly 25. So we set the value of the minimum, add it to the difference of the maximum minus the minimum divided by 2. The value of the maximum subtracted by the minimum gives us this region right here. If we divide it by 2, it gives us this subsection right here. We add it to the minimum to rescale it in the current Cartesian plane that we have in the horizontal axis because this is 0. And now we have a new bar, minimum plus half of the previous difference we calculated, which is equal to 6.55. 6.55 squared is bigger than 25. So we set the candidate back to the maximum. And if we repeat the process many times, eventually we're going to arrive to calculations that are closer and closer to the square root of 25.